So it's a pleasure to introduce our guest speaker today, Michael Wehner, who's a staff scientist at Lawrence Berkeley National Lab and a climate scientist. In fact, he specializes in what are called extreme weather events, and I hope you get to see some cool videos of that. Things like heat waves, intense precipitation, and tropical cyclones. So he was a co-author of the last IPCC report, the International Intergovernmental Panel on Climate Change, which is where all the countries in the world who still believe in climate change get together and write a report on what's going to happen. He's just been selected to be on the 6th committee as well, and he's testified before Congress a number of times on this topic. So we'll get to hear what the future looks like. So welcome.
Thank you, Jim. And I'm going to sit down because I've had a cold. So I'm going to talk about climate change and how we approach this. And you know, like any science, you know, one has some theoretical underpinnings, as well as in this day and age, lots of computational modeling. But first, I'd like to start out with a quote that I like from Ed Lawrence, but possibly Richard Heinlein, the sci-fi writer, defining the problem. So climate is what you expect, weather is what you get. And I like this definition because weather is the noise of the system, the day-to-day variations in the state of the atmosphere. It's what we live in. So we live in the noise. Climate is the long-term statistical description of the weather. So it's not just the average, but it's also, say, the extremes or the variations. And so this is a good starting definition. Now, computer science is where I'm going to focus today, although these are both very rich topics. And both of them are important applications for the largest computers built in the world. In fact, some of the early computers at Princeton just after the Second World War were applied to weather prediction and solving that problem, or not solving it, but providing useful forecasts of the weather is one of the most important things you can do with a computer. It saves many, many lives. You know, the forecasts from the National Hurricane Center are remarkably accurate and allow people lead times, you know, of several days to even a week to prepare for those kinds of disasters. But climate is a different thing. Climate change is a much more slowly unfolding disaster. We're about a degree warmer than before the invention of the steam engine, industrial age. And that trend is going to continue for the foreseeable future of this generation, probably the next, and maybe the one after that, in my opinion. But speaking of opinions, I have to give you a disclaimer that everything I say today is my opinion and not that of the United States Department of Energy, the Lawrence Berkeley National Laboratory, or the University of California. So Jim made a reference to the countries that believe. There are a lot of people who don't believe. This is a bad thing. It's a good example of how disinformation and misinformation can spread into the public and actually into politics and influence our society. But the IPCC, the Intergovernmental Panel on Climate Change, which I was a part of in 2013 and will be a part of this year and the next two, wrote that in 2001, an increasing body of observations gives a collective picture of a warming world and other changes in the climate system. And there is new and stronger evidence that most of the warming observed over the last 50 years is attributable to human activities. Now, these are very carefully measured statements, but they also were a long time ago. In 2007, which is now a long time ago as well, the IPCC wrote that warming is unequivocal. I had to look up that word. I didn't know what it meant. It means that it's without a doubt. And in fact, we've come up with a language to describe the warming and the source of the warming as extremely likely due to to human activities. If you Google me and you go to my website at the laboratory, I have a statement that I made at the American Geophysical Union based on the 4th National Climate Assessment, which came out in the fall of last year, as well as a link to a video where I, if you fast forward to the part of me, I forget where it is, you'll see me make a very strong statement about the source of the observed warming of the last 50 years. It is humans. There's just simply no other explanation that is credible. And we have lots of lines of evidence for that, one of which is computers, but we'll get into that in a minute. One thing that no one can possibly argue with is that carbon dioxide is increasing in the atmosphere. This is a plot since the time of Christ to 2000. And you see that in the red line, nothing like it ever happened in the past 2,000 years. And then all of a sudden, we started burning coal, changed the atmosphere composition dramatically. The upper right panel is temperature measured by thermometers since the middle of the 19th century. And the black line is a running average, and you can see that there's a trend of increasing. Right now, as of today, it's about just a fraction over 1 degree centigrade over the base levels of the mid-19th century. We have other ways of measuring the temperature of the planet through reconstructions. We call that paleoclimatology or paleo-reconstructions. This is like drilling into Greenland ice cores and analyzing the dissolved gases in the ice going back 20,000 years, or looking at isotopes in corals or other kinds of fossils or tree rings and that kind of thing. And you see, this is what's called the hockey stick. It's controversial for reasons that don't make any sense to me anymore, that show that in this case, over the last 1,000 years, the temperature is unprecedented. In fact, these things have been drawn back for about 500,000 or a million years, and there's no human that ever lived on a planet as warm as this before you guys. Not only that, looking around the room, I can make a statement that no one in this room lived in a year that was at the average temperature before the invention of the steam engine. I did, because I'm 61, and climate change really started taking off in the 80s, and natural variations means there's some up and down. You see that in these pictures for the global mean temperature. This is the annual average of the global average, but you guys haven't. So the key question, it's really a fact that the air temperature is increasing. I mean, you'll see, the last dying gasps of the contrarians trying to cast doubt on this, but it's just not the case. And in fact, fewer and fewer, even Chevron admits to this now. They just did it in a court case last month. The key question is this warming due to humans? And it's really a signal-to-noise problem. How do we compare this trend to variations on all sorts of different timescales? From the annual to the decadal to the centennial. And then understanding the causes really would increase our confidence in this, and the attribution of this warming to human activity, the human burning of coal and oil. And then, analyzing the past is only so interesting. What we really want to know is what's going to happen. And in particular, and this is again where computers come into play, because we make projections of the future, what will happen where I live? That's what everybody always asks me. It's a good question. That's what I like to know too. So the evidence for this is not just in temperature, it's quite multivariate. Here's 10 things we wrote in the 3rd national assessment. We could have probably made about 25 of these, but the graph would have gotten too complicated. these are things that actually a lot of these I was involved in. The water vapor is measured very accurately by satellites. We wrote a paper on that around 10 years ago or so, and as well as the satellite measurements of air temperature near the surface in what's called the troposphere. But also things like rising sea levels, the sea surface temperature, the ocean heat content at depth, declining sea ice, glaciers, snow covers. All these things have had rigorous analyses showing that there are observed trends and that these trends are attributable to humans. Well, this stuff is not rocket science. It's really actually steam engine science, ironically enough. These guys from Fourier, Tyndall, Arrhenius, and Callendar were some of the pioneers. What Tyndall did is, and Fourier before him, measured the radiative properties of gases. You know, they're all clear, so, you know, why are they different? You know, how could they be different? Well, it was a good question in the 19th century. Tyndall showed that they were different. He showed that carbon dioxide and water, being molecules with 3 atoms in them that can vibrate in many different ways, are more effective at trapping infrared radiation than simple polar molecules like oxygen or nitrogen. And in fact, this guy Arrhenius in 1904 wrote about something we still calculate today called the climate sensitivity. The climate sensitivity is defined in an equilibrium sense. How much would the planet warm if we doubled the amount of carbon dioxide? And he wrote about 5 degrees, and in the IPCC in 2013 wrote a bound on it of 2 to 5 degrees. So he was right there in apparently it took him 2 years to do the calculations, you know, by hand. The thing that I only just learned is what he understood, and is really remarkable, is that the temperature of the planet is not linearly dependent on the atmospheric carbon dioxide, but on the log of the carbon dioxide concentration. And you know, I bet you could talk to a bunch of climate scientists who may not even know that. And Arrhenius knew that 10 years ago, which is, I think, really, you know, shows how long we've known about global warming. Now, we seem to have forgotten in the middle of the 20th century for a variety of reasons. One of the things we use models for is to do what we call fingerprinting. This set of graphs is one I like to use to tell you why the observed warming is not the sun. And unfortunately, I don't have the observations on this. But the observations are I'll describe them, is that the lower atmosphere, the troposphere, warms, and the stratosphere, that's above where airplanes fly, is cooling. Satellites show that, balloons show that. It's without a doubt. You know, you have this pattern of warming and cooling in the vertical structure of the atmosphere. These are our plots with height on the y-axis and latitude on the x-axis, averaged across all longitudes, and various simulations. And the one at the bottom, we change everything that we know has changed. So we changed the carbon dioxide, we changed something called sulfate aerosols, which are a cooling effect from burning sulfur coal. We changed the sun, we changed the volcanoes, and we changed ozone, and various patterns. And the one that matches the most, of course, when you use everything, and the most dominant contributor to that is the greenhouse gases. And in fact, if you look at the sun, which is this lower left one, the bottom, you'll see that it shows a very slight warming everywhere. Well, it wouldn't explain the warming at the surface if that was all you had, because it's not enough. But let's say, you know, for sake of argument, that it was. It's still the wrong pattern. It warms the stratosphere when the stratosphere cools. And we can attribute from this kind of calculation that cooling to increases in carbon dioxide, principally, although the ozone matters a little bit too. Here's a, excuse the title, but this is a rather graphic example of how we can think about the sensitivity of the climate to carbon dioxide, trying just to do some curve matching. And so these are various effects on the atmosphere that can be calculated analytically. So you've got volcanoes are the blue lines, the sun's the red line, and the humans are the red, or the sun's the green line, and the humans are the red line. And if you go back to Tyndall and as well as an article by some colleagues of mine in the lab, you can vary this human activity. And so if we say, okay, there's no sensitivity, we get a curve like this. Oops, let's see if I can go this. So we keep on impacting this or changing this climate sensitivity. And in this case, 0.8 units with a funny name. I think 0.8 is this one. And so from the curve matching alone, we find that that 8/10, a best estimate of the observed 1 degree of warming is that 80% of that is due to humans. In fact, there's an uncertainty range on this, and it goes from about 80% to 120%. You say, well, how could there be more human warming than actually observed? And that could be that there could be a natural cooling cycle that we could be in that we can account for. All right, let's go into projections. Here's some really old projections, but they show the point. So the models are the green. It's an ensemble of 30 or 40 different climate models across the world, all of whom ran the same controlled numerical experiment. The black are the observations, and you can see that the models do a pretty good job of recreating the global mean temperature. And then in the future, I've got two curves, red and blue. And these are two different, this is why we call projections of future temperature projections and not predictions, because there's an if statement in this. So the red is, this will be the temperature if we're on a high emission scenario. The blue one is the global mean temperature if we are on a low emission scenario. And that's what's the difference. That's the big difference between a prediction, like a weather prediction, and a projection. It's not a prediction is not conditional. It will. There is a 20% chance it will rain tomorrow. There's no if statement in that. Whereas here, we don't know what humans are going to do, and so we have to make some assumption about that. Here it is on the scale going back, almost 1 million years. And this is one of those shows that we're way above the temperature in 2008 than we were for the last 800,000 years. And by the time you get out to 2100 under a high emission scenario, you know, you're looking at dinosaur times before it was this warm. So tens or hundreds of millions of years ago. Well, I made the point that, you know, we care about what's happening where I live. Well, we live here, somewhere in here, most of us. These are different scenarios, different human activity scenarios that we analyzed. The old ones are what I showed you the global mean plot before. Those are the ones on the left. The blue one was the top one, and the red one was this bottom one, or the second to bottom one on the left. The more modern scenarios are on the right, and we'll probably redo these again for IPCC, I expect. The bottom one is what I call the no policy scenario, and that's showing that at the end of the century, over most of the northern U.S., the average temperature is 6 degrees warmer centigrade. That's, you know, like 12 degrees Fahrenheit, which is kind of a lot. A lot of that changes in the winter. which means that, snow probably is not going to happen much in that kind of a future in most of the U.S. Storms might be more violent for other reasons, but they might not be snow. The top one, disabled RCP 2.6, that's a geoengineering solution. That's one that's trying to stabilize the global mean temperature at 2 degrees above the pre-industrial. And you'll see that, that means is that, you're between 2 and 3 degrees warmer over the United States. But that's not from pre-industrial, that's from essentially now, so that's like 3 degrees warmer than the pre-industrial. Reference periods can be confusing in some of this stuff. For the national assessment, they didn't want to know what's the temperature change from the pre-industrial. They want to know what's the temperature change from now, because now is what we live in and presumably reasonably adapted to. Precipitation is a lot harder to project than with confidence than temperature, because unlike temperature, which only mostly goes up, precipitation can go down. So some places get wetter, some places get drier, some places don't change at all. These are the projections from the third national assessment. The fourth is essentially the same for the 4 seasons. And you can see there's a seasonal difference. There's not much change in the fall or even in the summer. Big changes are in the winter and the spring. I've denoted 2 kinds of regions here. The areas that are hatched are places where I have confidence that the changes are large compared to natural variations in the seasonal mean precipitation. Areas that are whited out, the human change would be small. And so that's why you see in the fall there's not much change at all actually in the United States, maybe a little in Florida. But what stands out is the moistening in the winter and spring in the northern latitudes, and the drying in the southwest in Mexico. Well, why is that? Well, part of it, at least the part in the north, is that warmer air could hold more water. And so these winters that had been brutally cold are not so brutally cold anymore, but that means the air can hold more water, and so you get more storms. But you might ask, well, it's warmer in the southwest too. That's what you just showed. Why is it going to rain more there? And this actually holds for the north too. There's a circulation change. These tropics expand. This changes areas of what they call downwelling, which are some of the dry Mediterranean regions, and so there's a shift in these winter seasons. And so, and this is true also in Europe, in the Mediterranean countries there as well, in Italy and Spain and Portugal, Greece, Turkey. So the point I'm trying to make here is that this projection actually I have a lot of confidence in, despite its complexity, because not only do the climate models show some consistent signal, we understand the reasons for it. And I think that's really the most important part to aiding confidence in these projections of the future, is understanding why. And the models only tell us so much, and so, that's where, we still have to go in and think about what the answers are, not just read them off blindly. Excuse me. So, computations. Historically, climate models, and they still are limited by computer speed, and climate models groups have had access to some of the best computers for a long time. I started in this business around 1990. At that time, it took a year to simulate 1 decade with just a model of the atmosphere. And the typical resolution was several hundred kilometers. So the grid that you broke, we'll talk a lot about grids in a minute, was 400 or 500 or 1,000 kilometers on the side. So really, really crude discretization of the planet. In 2015, models that are about 100 kilometers on the side can run, a decade in an actual day. So and these models are substantially higher resolution, of course, but they're also more complicated. They have oceans and whatnot. I'll talk about that in a minute. it's still pretty lame, actually. The efficiency is low. Typical fraction of peak speed is 3% or less. If you got 10%, you'd be an all-star. Nobody does. Except maybe the European Center. We'll talk about that in a minute. My own work is focusing on much higher resolution on 25-kilometer models. It's a quarter degree. I get about 1 day per year on, well, in 2013 I got that, and I still get that. There's been no real increase in throughput for a single run, but the machine now is a lot bigger than the old one, so I can do ensembles of runs. I can do many runs at once, and that helps. But it's still pretty lame. In my case, I'm limited a lot by I/O, but the efficiency is still like 2-3%. And there are reasons for that, none of which are good. None of which are a good excuse. And even the 25-kilometer model is not high enough resolution. I would like to see us get to 1 kilometer. And the reason for that is clouds. There are no 25-kilometer clouds. There are no 100-kilometer clouds for sure. And so in order to represent the cloud processes, we have to do something they call parameterization, which is some approximation of the subgrid scale processes. You might have heard about turbulence modeling. Turbulence modeling is the same kind of thing where you can't resolve all the scales of turbulence, so you have some kind of approximation for these processes that are not resolved. And so we have to have such an approximation for clouds. In my opinion, there's been no fundamental advances since 1978 in the paper of Arakawa and Schubert. We've had a lot of papers, we've done a lot of studies, but there's been no fundamental advances since that time. In my view, the right thing to do is direct numerical simulation. At a kilometer, you still aren't resolving actual clouds, but you are resolving cloud systems. And I think that we can, if we had the resources, we could demonstrate that these things would be superior in a global model. People have been demonstrating in local area models of, say, just the Western United States, or just the Midwestern United States, actually. There's a good study on that these models are substantially improved. I wrote a paper. If you go to my website, you can find it somewhere, or you can search for Green Flash. That was the name of the project, and Berkeley. And what we did, we estimated that we needed 28 petaflops sustained at to run a model at a relatively slow throughput rate, but something that was just barely fast enough to do some science. At 2% efficiency, this doesn't make it. You're looking at exaflop machines. And so we came up with some hardware, what we called hardware-software co-design, to basically build a customized machine for this problem. And we actually think at Berkeley, so a group of us had to do it at Berkeley, think that this is the way to advance through the next couple of decades, is that the day of the general purpose machine will become less interesting for the biggest and most challenging scientific problems because of efficiency issues of scaling. These machines have a lot of the reason why our efficiency is so low, some of the reason is that we don't use a lot of the operations that are in it, and so that are in the processors, and so by reducing that kind of waste, we can increase efficiency and reduce power demands, which is a big issue in the exaflop and beyond kind of computational world. We need to get to at least 50 kilometers in the ocean, but I think we probably want to go to 10 kilometers again. And like I said, one of the things that has happened is I can make more realizations, more integrations, run bigger ensembles. We need to make ensembles because that's how we characterize the variability. You perturb the initial conditions a little bit, the climate system's chaotic, and so after a few weeks, you have a completely different weather pattern, but the statistics, remember climate is statistics of weather, is going to be the same if I run it long enough. And so that's how we characterize the internal chaos of the climate system. Here's some results. These are old now, but they show the point that to get better answers, high resolution really helps. This is wintertime precipitation over the United States. Observations of this lower panel. 50-kilometer model captures the southeastern part being wet, whereas 75 kilometers, and at that time the state of the art was 300 kilometers, isn't even close. I'm interested in extreme weather. This is a measure of extreme weather called the 20-year return value. The 20-year return value is that value that you would expect to exceed once every 20 years in a long period of time, or it has a 5% chance of happening this year for the daily precipitation. And the observations are, again, the lower right, and here's three models, 200 kilometers, 100 kilometers, and 50. And see, when you get to 50, it's starting to get, a pattern that looks much closer to the observations than the 200 kilometer, which was the state of the art when I wrote that paper. And even really the 100. So now I'm going to go to a simulation that is the model I'm working on today. You can find this by searching me or FVCam on 5 on YouTube. Let's see if we can get this to work here. This is a 25-kilometer global model showing what an astronaut, if he or she could see in this projection, it could see water vapor. So it's a vertically integrated water vapor concentration. And what you see are, I'll stand up here. What you see are these filamentary structures, these things here. Every once in a while you'll see a big cyclone. Let's see if a hurricane pops up. Here's a hurricane right there. There's a big extratropical cyclone. But the point is there's a lot of detail. Now if you're in the back, you may miss some of it. In a minute it's going to switch to a 200 kilometer and 25 kilometer simulation at the same time, I hope. A lot of cool structure here. This is interesting. It hits the Andes and bounces off because the mountains are high enough in this. And you get the same in the Tibetan Plateau. You get some big storms going on there. This is probably the wrong movie. It's probably going to go on forever. Well, I'll describe what the 200 kilometer one would look like. Basically it looks the same, except there's none of this fine structure. That's a good thing. It means that a lot of the results that we wrote about in the IPCC and the National Assessment about large-scale climate change is true. It hasn't changed anyway by going to higher resolutions. But what this model does, because it has the tropical cyclones and other real extreme weather more realistically represented, we can start making projections about changes in extreme weather like hurricanes, for instance. So here is, in fact, a result showing the observed hurricane tracks colored from category 0, that's tropical storm, to category 5, which is an intense hurricane. Observed on the top and modeled on the bottom. I'm going to peel off the category 0. So this is just category 1 through 5. And you can see there are some good and bad things. The good thing is there's about the right number. The bad thing is there's too many in the middle here. And that's what in polite company one calls a model bias, but that just means it's wrong. It's model error. But so the bias is that we have too many in the middle, but globally it's getting about the right number, so we can at least ask questions about the change in the global number of hurricanes. And in fact, what's really remarkable about this 25-kilometer model, this is somewhat unexpected, and not without controversy, is that the model actually makes storms all the way up to category 5 on the Saffir-Simpson scale. The observations are on top again and the model on the bottom. doesn't quite make enough, and that's sort of what it was expected, because 25 kilometers for a hurricane is relatively coarse. So you have a question back there?
Yeah. How do you know the observed data is correct, that they're not missing hurricanes?
We don't. It's called the best tracks, and it's certainly prior to the satellite era, it has major errors. And people try to deal with that in various ways. One of the things you'll notice in that observed one is that some of these storms in the Pacific started the date line up magically. That's because those are analyzed by the Japanese meteorological services, and they don't track anything on the other side of the date line. Because those storms really did start somewhere east of that of zero longitude. But that is our best estimate of the observations. And observational uncertainty is an important aspect to consider when comparing climate models to observations. How well can you possibly, what is the standard? For other kinds of storms, we do not have such analyses. I made reference to, excuse me, extratropical cyclones, and there's over 1,000 of those per year globally, but we don't know if it's 1,000, 2,000, or 3,000. We just don't know. So that makes model analysis somewhat more difficult. So like I said, it does pretty well on the observations. The total number is about 90. The model makes close to that, and it's within the interannual variations. The hurricanes category 1 to 5, the observations are about 50, and the model's about 50. I don't have it here, but the observed category 4 and 5 is about 15 per year, and we're about 8.5. So it's a little low, like I said, would be anticipated. Now, one of the challenges of finding the storms. Now, it's hard enough to find the storms in real life where they're unfolding, one day at a time. In the computation, of course, we're trying to make, I'm making 365 days in a day. I'd like to be making 10 times that. And sometimes I am if I'm running 10 runs at once. And so the volume of data is too large to do it by hand the way that the Met services do it for the observations. And so we need an automated way to do this. Unfortunately for hurricanes, they're well enough established that, or well enough defined that one can have what I call heuristic algorithms to identify these things. But and we have software for this. It does really well for category 1 through 5. Category 0s, the storms aren't so well defined. It doesn't do as well, quite frankly. And there's a whole literature on different ways of counting storms. One of the things that I've been doing with my colleague Prabhat, and I don't know if he's spoken to your group or not, is to use machine learning techniques, convolutional neural nets, to track storms. And because we have a reasonably good storm tracker for hurricanes, we've used that to prove the principle. So far, we've applied it with remarkable success on hurricanes and atmospheric rivers, and which atmospheric rivers are another one where we have a whole bunch of different algorithms to detect them. How well they work or not is another story. The machine learning can certainly mimic these. But there's another kind of storm front where we do not have a heuristic algorithm to identify storms. These are called frontal systems. And you'll see that when you watch the television news guys, they'll show there's a cold frontier, and they'll show a line. That line is drawn by hand. A colleague of mine at NOAA, National Ocean and Atmosphere Administration, had his group spend 5-person years analyzing the United States for frontal systems and other kinds of extreme weather since like the 1920s to now. So we have a handmade set of curves that we can use as a training data set for the machine learning algorithm, for the neural net. And not surprising to them, but very surprising to me, it works really, really well. And in fact, the machine learning algorithm works better than the human algorithm. You can see this by looking at it. The humans make two kinds of errors: sins of omission, where the meteorologist simply got tired, or they don't draw the frontal systems long enough. The lines they draw on the maps are too short. The machine doesn't make those errors. We're now in the process of writing that up, and this will be, I think, one of the first demonstrations of something that you can do, a climate change problem you can do with neural nets, convolutional neural nets, that you couldn't do any other way. So it's pretty exciting times. These are pretty big data problems, multiple tens to hundreds of terabytes of model input. If you're interested in that, again, go to my page or Google myself and Prabhat on YouTube, and we have a lecture that was at an Intel high performance code developers conference just last fall. Most of it's Prabhat, so it's actually a very good lecture. Not the same as this one. All right, what else? All right, so I told you we could find hurricanes, we could simulate them, so now I can run them in warmer worlds and weaker worlds, or warmer and cooler worlds. So the blue one is basically today, showing there's not quite 90 storms per year from category 0 to 1, or 5 rather. And the red world, ignore the other two, the red one is a 2-degree warmer world. And you can see there's a substantial decrease in the number of hurricanes globally. But that decrease is only in the weak ones. And in fact, if you look at the category 4 and 5, the so-called intense hurricanes, there's actually an increase in those. So the most destructive hurricanes become more frequent, and in fact, the strongest ones become stronger. The weaker ones become less frequent. Now that is a projection, has some confidence statements that need to be made about them. The part about the Cat 4 and 5 storms becoming more frequent and more intense, we actually have a lot of confidence. I think the community agrees on this quite across the board, for theoretical reasons. There's more energy. When you have one of these storms, it's really kind of a perfect environment for it. There's more energy in a warmer world, and that gets reflected in the hurricanes. The other part of it, what happens to the weak end, the low end of the tail of the distribution of these storms, is actually quite I wouldn't say controversial, but it's still an emerging science. Most of the models project this. There are other models that are at this range. One or two don't. And some of the theoretical arguments are not completely clear as to why this might be the case. So that part of the projection has a lower confidence statement to it. In the national assessment, we wrote that that the number of weak hurricanes will either stay the same or go down to try to I don't think anybody thinks there's going to be more, but in these policy relevant documents that involve lots of authors, one has to negotiate the language quite carefully. It will rain more in these storms across the board. My colleague Mark Risser and I wrote a paper that came out in December about Hurricane Harvey. That was not a modeling study, that was statistical analysis, but there are modeling studies that go with it from other groups. And basically all the groups that have looked at this agree that climate change made the rains in Hurricane Harvey larger. In our case, we wrote a statement that our best estimate was that climate change caused the precipitation to increase by 38%, and we put a lower bound of 19% on that. So those are kind of big numbers when you think about how much rain actually fell, like 5 feet in some places. The floods were devastating, and they were just made more so by climate change. High resolution is expensive. I only used 8,000 processors, but that first calculation took 5 million processor hours. Last year I used 70 million processor hours on the Corey Knights landing machine. That's a relatively small percentage of all the cycles, but for one individual, that's a fair number. This year I'll probably use only 50 million because I'm trying to write papers instead of just turning cranks. It's a lot of effort actually to run this many, to produce this much data. My colleague and I made about 4 petabytes of model output in 3 or 4 years, and the data management problems are big, as you might imagine. Oh, here's the paper on the green flash, which is, I wrote this 5 or 10 years ago that machines in excess of 10 million processors are 5 to 10 years out, so my projection was pretty lousy on this one, because we still aren't there. But I do believe that that's where we're going to go. This may be interesting to some of you. I had one more movie to show. Hopefully this one will work. All right, so this is going to show an atmospheric river hitting California. The water vapors, that blue kind of stuff again, the colors are precipitation, the arrows are wind vectors. And the cool thing about this is that it shows that the mountains matter. The average elevation of a mountain is dependent on the grid cell. You know, it's the average in the grid cell. So a 100-kilometer cell is going to have smaller sierras, lower sierras than I can't make it stop there. But what I wanted you to, well, we can make it run again, I guess. What I want you to look at is, at the end, all the precipitation, that's the colors, are falling on this side of the Sierras. And that's realistic. And it's because in this model, the mountains are high enough that it can do that. If the resolution is too coarse, the storm's going to go right over the low mountains and it rains in Nevada. That kind of bias, that kind of error, I can't fix. So it's really, this I think, there you see it there. It's all on this side of the Sierra. Now, what's happened since I made this model this run is the model's gotten a little bit better. In this model, the rain only falls straight up and down. In the real world, there is some transport horizontally where wind blows some of the rain horizontally, and that is now incorporated in the latest version of this model, which I haven't yet run about. All right, so let's talk about how climate change is modeled, how you model the climate. You gotta have a lot of stuff in a modern model. You have to do all these atmospheric processes, you have to have ocean processes, you have to have sea ice, you have to have biological things going on in both the land and the ocean. There's atmospheric chemistry, you know, energy transport, moisture transport. These have to be conserved. That's what's different between a climate model and a weather model. In a weather model, you don't really have to conserve energy because the algorithms are good enough that after 10 days, you know, you haven't lost enough energy, but if you run a couple of centuries and you're just losing a small fraction of the energy in the system, you will drift into a climate state that isn't realistic. So here it is in words. The atmosphere is the most computationally expensive part. It actually has 2 parts: the dynamics, which is the solution of the Navier-Stokes equations, the equations of motion, and then all the stuff that's the subgrid scale, like the clouds, for instance, and also turbulence, some of the radiation transport as well. In the ocean is mostly dynamics. There is some turbulence that has to be accounted for. Computationally, that's not a big deal. And the sea ice is kind of interesting because it's also, you know, I mean, not think about ice as a fluid, but it is. It's a viscoelastic fluid. It can deform if you put a stress on it. I witnessed this about 20 years ago at Los Alamos National Laboratory. A guy named John Dukowitz and Richard Smith came up with a new rheology that revolutionized the modeling of sea ice. And so it's really kind of one of the exciting things to witness, even if you're not involved, if someone else is doing it, some change that radically improves their science. And that certainly happened with ice. I'm going to show you a movie about the big glacier on Antarctica. Greenland would be a similar kind of situation, it's much smaller. Like I said, the land model has to do biology and the moisture and energy budget. And then chemistry can be very expensive too. Some chemistry models have as many as 100 or more radiation or chemicals that are transported, and you have to do reactions on it. So why is this expensive? Well, it's that you have a lot of grid salt points. If I was going to do a 1 kilometer discretization, there would be, including all the vertical and everything, there are 2 billion cells. The time step would be 7 seconds. At the 25 kilometer, the time step is 450 seconds, which is a couple of minutes. I forget how many minutes that is. There are a lot of 450-second periods in a century, so it's just a very grinding process. The codes are complex. They're old. They're written in Fortran largely. Some are written in C. Nobody writes in Python. Although people are starting to write shells in Python that drive some kind of C++, C underlings on it, but the compilers are fastest in Fortran. And so, and some of these codes are legacy. Sometimes the person who wrote that is retired or dead. That's how old these codes are. That's not a good thing. That's a function of money. Just priorities have always, climate change has always been a science that's under a lot of stress. We want to know the answer now, and there's good reason for why we want to know that. And so long-term investments are sometimes difficult to sell. And I think that's actually haunted us. So anyway. So this is from a colleague of mine, Dan Martin. I don't know if he's going to speak to you guys or not, but I'm going to show you his movie. Here's a code called Bicycles. Icicle was a project, and Bicycle was just Berkeley in front of that, which we thought was pretty funny. His uses what's called adaptive mesh technologies, where you have a resolution that not only is it variable, but it can change depending on how the system evolves. And as you'll see in this movie, and hopefully it'll start now. This is Antarctica showing the flow speed, the velocity of the ice. And is it running? It should be running. It's a very slow movie. Maybe it's running now. Yeah, there it is. So here's the initial state with the mesh showing a fine resolved mesh in the purple. Here's the velocity again. It's going to start in a minute or a second, and you can see the ice melt back rather dramatically, actually. And then the resolution adapts to, as that ice melts back. Now the thing about the flow speed that shows why you need that is all the action is around the edge. The blue is slowly moving in the middle. I think this is running at 500 meter resolution. I'd like to see it do 250 meters. But in the middle, it's like 5 kilometers because things aren't moving there. You don't have to have the resolution. So that actually, is one, in my view, is the state of the art for modeling the Antarctic ice sheet. And in fact, excuse me, that amount of ice meltback would be devastating in terms of sea level rise, because that ice then melts and goes into the ocean, and there's just more water in the ocean then. So lots of stuff to calculate. That's why, and these models are complex, that's why the successful modeling groups are really highly interdisciplinary. They'll have atmospheric scientists, ocean scientists, biologists, et cetera, and of course, computational scientists. And nowadays, data scientists, which I think is a relatively new thing. And so not everybody has them. We have a few. All right, finally, I'm going to finish off with just an example. It's a CS class. I should show something that illustrates how to build a model. And so just a simple thing, let's simulate the dynamics of the atmosphere, and we're going to discretize a sphere and apply the equations of motion, which are the Navier-Stokes equation. Let's just think in 2 dimensions. latitude and or horizontal dimensions. So the easiest one is a latitude-longitude grid. And in fact, the movie I showed you of my calculation was on a latitude-longitude grid. It's uniform in the two angles, the two solid angles that define spherical coordinates. The problem, of course, is you have a singularity at the pole. This is a polar singularity, obviously. And that means is that we're going to have problems with the time step. Now, what limits the time step, I mentioned it's 450 seconds, I think, in my calculation, is something called the Courant stability criterion, which is a relationship between the grid spacing, the maximum wind speed, and the time step. As you can see, it's the grid spacing divided by the wind speed. Wind speed maximums on the planet are the jet stream. It's like about 180 miles an hour or something. And so that's what the controlling time step is. If you violate this condition, the code will be computationally unstable. And you'll then have to either damp it out with some kind of a filtering algorithm, or the code blows up. My code blows up depends on how warm it is. The warmer it is, the slower the atmosphere goes. The simulations, paradoxically, are somewhat more stable. My code blows up on a Courant instability about once every 3 simulated years, maybe 4. And that's because we're just a little too close to the edge. And that's a balance between computational speed and this problem. What happens when I do that is I back it up, I give it a little perturbation, and you get past that violation. It's not the best solution. Other algorithms are more robust to this, but it's mainly because of this convergence of the meridians causing these grid points to be too long and skinny, high aspect ratio towards the pole. Another problem is that sometimes you have cross-polar flows. That's important it's important a lot in the winter. And some of these big storms we have, or cold spells sometimes involve, in the United States, would involve a cross-polar flow. Flow through a singular point is difficult numerically. And not all the models do a very good job, unless any of them do. All right. Let's see. Okay. I'll skip that one. So there was another, the historical way of solving this polar problem is to transform onto spherical harmonics and map the Navier-Stokes equations onto a spherical harmonic coordinate system. And it's really elegant, and until about 10, 15 years ago, most of the models use this. And in fact, the European Center for Medium Range Weather Forecasting, who are probably the best in the business, still use this code. And one of the reasons why we thought 20 years ago that it would be obsolete by now is that you have to calculate the Fourier and Legendre transforms. And these don't scale well. They also we're not in a regime where we have parallel FFT algorithms. They're not high enough wave number for parallel algorithms, so they have to be serial. But the European Center, which did invest heavily in computational scientists, have solved this problem and have managed to keep this alive. It's hard to know how much longer they'll do it. I mean, I didn't think they would, so I'm not going to doubt them any longer. But it is certainly an issue that as you replace these difference equations with these transforms, the computational burden then becomes calculated. Here I've got some scaling. You could go, if you chose the discretations to be powers of 2, you can use fast Fourier transforms. They scale as m log m rather than m, but that m log m is still super linear, so that means that when you double the resolution, it's more than twice as expensive. back when we had vector machines, they were very fast. Sometimes vendors still can supply, depending on the vendor, will supply fast algorithms. These algorithms they're kind of my generation back in the old Cray days. That's when these things really were developed, and those vendor FFT algorithms really made this in the 1980s the state of the art for both weather prediction and climate. There are some disadvantages. This is my favorite one. Besides the scaling, is that you can have spectral ringing. It's a Gibbs phenomena that's well known with these kinds of FFTs. And so if you see here, this is South America. So the Andes are here. You've got this nice high precipitation near the Andes, but you also have some rain coming right off here, a shadow. That's completely numerical. And just basically a reflection of the FFT off of the Andes. So analysts have to understand that when you're analyzing these results. Like I said, I would have thought that this was not going to be today, but it still is. The European Center basically does a global redecomposition of the atmosphere 3 times, of all the state variables 3 times, in order to have each one of these be as computationally efficient as they are. So one has to have a machine with very good interprocessor communication, because the volume of data being transferred between processors is much larger than in grid point schemes, where you have the classic halo kind of domain decomposition. They can't use domain decomposition. But back to discrete, finite difference, finite element kind of methods. This is another one I think is really interesting. It's called the icosahedral mesh. The icosahedron is that figure on the structure on the far left. And if you bisect the vertices of the sides of the triangles, you can make a grid out of it. This is bisecting 4 times. It has no polar singularities, but it does have 6 special points where the connectivity is different that in each hemisphere that correspond to the original vertices on the icosahedron. This is what we wrote the green flash papers on. Is we did that bisection 11 times to get to, or maybe 12 to get to 2 kilometers. It's in some ways it's a very nice mesh and it's spatially uniform. The area difference between the smallest and largest mesh is never more than a factor of 2, whereas it's much larger, say, for that latitude longitude grid I showed. The connectivity is complicated. It's not explicitly logically rectangular, but there's an underlying logically rectangular connection that you can use. It's in operation at Deutsche Wetterdienst, and as well as at Japan. And the Japanese have really pushed this. They've run this model with, I think, 14 bisections, getting down to 400 kilometers globally on a machine called the K machine. They actually achieved almost a petaflop sustained performance, which was a record for an atmospheric global model, but it wasn't faster than real time. They could do 24 hours actually, it was the same as real time. I think it was faster. I think it was they could simulate a day in 18 hours, which isn't really fast enough for even weather prediction. But the fact is they did it. Another interesting grid, and this is the grid that I'll probably be moving to because there's a couple of models that I don't write models anymore, but there are models available. It's called the cube sphere. Now, if you imagine the icosahedron one as a child's toy that you drew this bisection on, and then you overinflated it to be a sphere. Now do that with a cube. So you have a child's toy that's a cube. Draw a grid on each face, and then pump it up till it's a ball. This is what the grid would look like. It has special connectivity points too that go to that are traceable to the original corners of the cube. It's not quite as spatially uniform if you drew these grids to be orthogonal, but actually what the guys do who run this kind of model is they relax that orthogonality and have cross terms in the solution of the Navier-Stokes equations, and it's used in some powerful models. The beauty of this and the other icosahedral discretization is it scales well with processors, much better than the codes that I have. Part of that's by design, but instead of running at 8,000 processors at 25 kilometers, I would expect to run these at about 30,000 processors. And it could probably run more, except that the I/O isn't very sophisticated, and I'll just be I/O bound, and so then I'm wasting resources there. Another thing that's interesting that people do with grids is variable resolution. This is variable resolution on this grid. You see two meshes here, one refined within the first refinement and then a second refinement. These are statically refined. The adaptive mesh that I showed you before can vary. That's a higher state of the art than this. This is a fixed but varied resolution, or non-dynamically variable, I guess. And it's good. There are pros and cons to it. I think for my purposes, they have limited uses, one of which is analyzing individual storms. This was a calculation where we did this kind of mesh, except instead of being over the U.S., we put it over the Philippines and calculated the Typhoon Haiyan. And then we did some climate change perturbations to it to try to find out the influence of climate change on Typhoon Haiyan. We started out with 70 kilometers and refining 3 times all the way to 8 kilometers. And here's just an example of some of the simulations. The observed track of the storm was the black line, and I think the red one is our simulation with some initial condition perturbations to get a spread of what they call a hindcast, not a forecast, because the event's already happened. It's a hindcast. This is some of my latest research where we're trying to analyze the effect of climate change on this storm by producing hindcasts that are a hindcast of the storm that was, and the hindcast of the storm that might have been had humans not perturbed the climate system. So we perturbed the hindcast that was to remove the human effects, and you get a spread. All right, so I'm just going to be done here. I just wanted to show that there's some really weird things you can do in ocean modeling, which is different than atmospheric modeling, where you have to cover the whole planet. You don't have to cover the planet for ocean model where it's land. And so one of the things that they did is they took the North Pole and they did an orthogonal coordinate transformation and moved the North Pole over Canada. And then you have latitude and longitude everywhere else. South Pole, you don't have a problem because Antarctica is right at the South Pole. And so this was a way of using a grid that looked like latitude and longitude originally and is in some curvilinear coordinate system very similar to it. They even had another one where they took the pole and they split it in half, and they made an east pole and a west pole, and they put one over Canada and the other over Siberia, and I think they used that for a long time. The advantage is that it looked relatively reasonably uniform in over Greenland and this part of the Arctic. But they've since gone to an icosahedral mesh, and that's an antique now. So the reason I went through all this, I mean, it may be tedious, is to give you this one lesson, is that modeling is always, no matter what you're modeling, whether it's a climate or stock markets, whatever, it's always a set of compromises. If you could do it exactly, you would do it exactly, and you just solve the equations. That's why you have to use computers, because we don't have the exact solution. And you have to take in a lot of different factors when developing a model, and some of it may be dictated by the physics of the problem. Like I mentioned, weather prediction, I don't care so much about energy conservation like in climate, because, the rate of energy loss isn't so important for weather prediction, but it is over the century scales. But you may also want to consider what scale you're in, what part of the world you're interested in. You might want to do the variable resolution. You might consider about accuracy. If I'm interested in precipitation of the United States, I really got to get those mountains so I don't have rain in Nevada instead of off the Sierras. And you also have to say, what kind of machine do I have? And there's a growing, whether you have GPUs or Knight's Landing kind of vector machines, or whatever it happens to be. The limitations of the machine are also something that, and especially if you can make some, if you have some idea of how the technology is going to evolve, that may serve really well. I've covered all this stuff. Large databases. We're now in the petabyte scale. We'll eventually be into exabytes. Data management is hard. One of the things that climate does as a discipline is we recognize that very few people actually have the resources like I have here at the laboratory, and that there are lots and lots of analysts out there who are hungry for results. And so we distribute the data relatively successfully to analysts across the world, at universities, graduate students to senior staff. My guess is that there are probably 1,000 analysts for every model developer. So that as the databases get larger, I think there's an unsolved problem, is how are we going to get climate model output into the hands of climate model analysts efficiently. You're not going to analyze 10 terabytes of data on your laptop. That's the practice now, is people will download the model, the download model output, they do it on their desktop or laptop. That's simply not going to happen. So I'm really advocating that we need some kind of cloud computing solution, but not everybody's hearing that. And I just changed this to be in red, the machine learning part, because that's such an exciting thing. So when I first started, they called climate change a grand challenge modeling problem, and it remains to be a grand challenge problem. I think that those words are no longer used because it's so old. I think we understand very clearly that humans are the cause of the observed warming, and we will undoubtedly warm, at least, in my opinion, at least another degree, probably another 3 degrees before any real actions are taken politically. The actions that need to be taken to avoid more than a degree of warming are drastic. There are essentially no actions we can take to avoid another degree, regardless of what you've heard about the Paris Agreement. So that part of the problem we already know. I think the part that's interesting, scientifically and as well as computational scientists, is getting to provide actionable information to people who want to make decisions. Whether they be in the corporate world or in the public world. I'm working with the San Francisco Public Utilities Commission, who are designing a new storm sewer, and they need to know how to plan for a 100-year investment, that kind of thing. So providing information, credible and confident projections of future climate at scales where decision makers can actually make informed decisions is probably one of the more exciting things that's going on. And so I had an editorial comment. Politics of climate change is ugly. I could give you all sorts of horror stories about that. And it's sort of a problem that my generation has identified, but we're still not doing anything about it. So we're leaving it to you guys, I'm afraid. Here's some additional resources. My email's at the bottom. The one in the middle, IPCC model data distribution, is how you get your hands on model data. Anybody can get model data, you can do it. I mean, you don't have to have any special permission. You just got to sign up and go through all the rigmarole that they have. You can download a model, actually, the Community Climate System model. And I think the best source for general information about climate change is this one, globalchange.gov. It's a little more digestible than the IPCC. So that's it. Thanks very much. And I think I can take questions if we still have time. Yes, please.
Do you ever apply these codes to trying to look at weather on other planets, like looking at?
Oh, I have not, but yeah, they're. So the question is, have climate models been used to simulate atmospheres on other planets? And the answer is yes. I have friends who have looked at Jupiter, different kind of planet because it doesn't really have a real surface. Venus, which is a much more similar planet. I don't know if people have done Mars. I'm sure they have. That tends to be a more academic exercise rather than a government lab kind of thing, simply because of funding issues, funding sources. But yeah, there's no reason why you can't just take one of these models and change the diameter to be Venus and change the composition of the atmosphere to be Venusian, and then when you might worry a little bit about the chemistry, but it's the downside of exoplanet climate simulation is lack of observations.
Sure.
I mean, you have little observations, but as poorly observed as the Earth is, it's better than Venus or Mars. Any others?
I have a question.
Yes, please.
So you mentioned that one of the reasons that you get such a low percentage of peak performance is that you're not using all of the operational units that are in the processors in supercomputers today. So like what is the composition? Are you doing mostly integer arithmetic? Why is it that the performance is so slow?
It's mostly floating point. When we well, so there's two reasons. One is we're not using all the operations, so there's some that's sort of a fundamental limit. But the other is that there's no one thing. Climate models are hundreds of thousands of lines, and there's no one algorithm that tends to be the biggest source of cycles. And so in order to really up the performance, one has to go through everywhere. And that's expensive. So one of the things we did for the Green Flash project is we used a technique called auto-tuning. Auto-tuning is kind of cool. I don't know if you've heard about it. It's developed here in this building. And the slide I have on this is great. It says it's a quote from Agent Smith of the Matrix, and Agent Smith said to was it Nemo or whatever his name was, never send a human to do a machine's job. And in some sense, tuning of codes is a machine's job. And so what auto-tuning does is you take a loop, and the human has to say, okay, it's this kind of a loop. And we looked at the buoyancy loop, which was the loop with the largest cache size in our code that we were analyzing. And the auto-tuner rewrites the loop 500 different ways or more, and then you run it, and then you could optimize then for a variety of things. We said, okay, let's optimize it to be the lowest cache. We reduced the cache size by like a factor of 1,000. But the interesting thing was that actually also reduced the computational costs by a factor of 2. And when we looked at the mix of instructions from the optimized version versus the original one, is the optimized one was almost all floating point operations, and the unoptimized, the human readable loop was, because the rewritten, it rewrites it, and so it's not really very friendly for humans to read. Machines read differently than we do. All the shifts and the non-floating point operations were cut down by to be essentially negligible, and so that was done. I don't know what we have now, but at the time we did not have software where we could apply this to the entire code. But that kind of pre-compilation optimization would be would actually help lots and lots of different kinds of codes, and so but it can, again, it only bought us a factor of 2. I mean, but a factor of 2 would mean I could do twice as many calculations. All right, I'll let you guys go.
Let's thank the speaker again.